Good morning everyone. My name is Sagar Vishkarma and my registration number is 24270300028 and my section is J and I am a CSE student of BTech. Let's start. Today I'll be presenting my case study on the Intel Core Skylake architecture and demonstrating the simple assembly program that generate the Fibonacci sequence. This presentation is divided into two parts. First, an overview of the Skylake microarchitecture and then short code demonstration. Let's move to the second slide. Intel Core Skylake is the Intel's 6th generation processor microarchitecture launched in 2015. It's based on CICSC complex instruction set computing design principle, which means each instruction can perform multiple level of operation. Skylake was built on 14 nanometer processor designed with better performance and power efficiency. It was mainly used in laptop, desktop servers, targeting the both everyday users and enterprise system. Its main strength to include stability, energy, efficiency, and high performance across multiple workload. Let's move our third slide. Instruction set architecture ISA. Next, let's talk about the instruction set architecture or IC. Skylake follow x86-64 instruction set which support both 32-bit and 64-bit operation. One unique aspect of this ISA is that instruction or variable length ranging from 1 to 15 bytes. It supports multiple addressing modes such as immediate, registered, direct, indirect, index addressing, giving programmer flexibility into memory access. Some common instructions include MOV for the data transfer, CMP for comparison, and conditional jump like JE and JNE for control flow. Arithmetic instruction are MUL and IMUL are used for multiplication operation. Let's move to our third slide. It's a supervised superscalar processor, which means it can execute multiple instructions per cycle. The architecture also support out of order execution, so instruction don't have to wait for other finishing before instruction feature like branch prediction and micro OP catch improve efficiency by reducing stalls and reusing decode instruction. Separate execute unit handle integer, floating point, and vector operation, which help improve throughout the performance. Let's move to our fifth slide. Memory hierarchy. Next is the memory hierarchy. Skylake user three-level cache system for faster data access. Each core has 32 KB instruction. Cache has 32 KB cache at level 1. At level 2, there is 256 cache per core, and finally a shared L3 cache that range from 2 to 8 MB per cluster. Skylake also support DDR4 and LDDR3 memory, which provide higher bandwidth to reduce memory delays. It uses hardware prefetching and memory level parallelism. Fetching and data, it's needed. Let's move to the sixth slide. Skylake also included several advanced features for performance and parallelism. It supports multi-core processor with up to 8 core per processor and simultaneously multi-threading, which allowed 2 thread per core. For vector parallel combination computation, it supports SIMD instruction like AVX2 and AVX512. These are useful AI graphics and scientific application. Skylake processor also includes integrated GPUs and rendering graphics workload. Other feature including virtual supports, hardware-based security, and improved power management. Let's move to the seventh slide. From historical perspective, Skylake was a major leap forward for Intel. It improved instruction per cycle or IPC compared to the previous Broadwell architecture while consuming the less power. When we compare Skylake with AMD Zen's architecture, Skylake typically has better single threaded performance, while Zen provide better performance efficiency multi-thread performance. Overall, Skylake maintained Intel's strong leadership in mid 2010. Let's move to the 8th slide. Fibonacci sequence assembly program. Now let's move to the second part of the presentation, the assembly program. Here we have written the some simple x686 assembly code that generate first 10 number are the Fibonacci sequence. The program initializes two variable a and b 0 with a value in 0 and 1. If then enter a loop where it prints the current value, add the two previous number and update them to the next iteration. The loop continues units 10 numbers are generated. This program demonstrated basic concept assembly programming such as data improvement, arithmetic control flow using loop and comparison. Let's move to the ninth slide, which is conclusion. When we run the code, the output is a Fibonacci sequence. Let's see, for an example, 0, 1, 1, 2, 3, 5, 8, 13, 21, and 34. To conclude, Intel Skylake architecture represent the perfect balance between the performance and efficiency. It introduces advanced technique like superscalar execution, out of order processing, and strong memory hierarchies. The assembly program reflect how these hardware features support efficient computation at the instruction level. Thank you for listening. This is end of the video. Thank you. Hello everyone, my name is Sagar Vishkarma and this presentation I will demonstrate my assembly program that is printed the Fibonacci sequence directly from the bootloader using BIOS interrupts. I wrote the code as NASM and ran into using the Bosch emulator. Let's go through the code and then see the output. Okay, let's overview the code. This is the full code. So let's move to the first part. That program is programmed with the line 0 7C00, which tells the assembler that is code that is a code will be loaded in the memory address 7C00H. That standard the starting points of the boot folder. This means the when the system is boot, our floppy image execution begins right from the address. Okay, let's move to the start part. This is first part. Okay, this is first part. The program first print a simple title message. The instruction move SIH message title load the address the message Fibonacci into SI register. Then using load SB, it read to each character from memory into AL register. Then using load SB, it reads each character from a memory and in AL register. It interrupts 0 by 10 with AH is equal to 0 EH. Prints that character on the screen tally tab mode. Okay. This loop continues until it encounters the null character, making end of the string. Let's move to ASM part. This is our ASM part narration. After printing the title, we move on the Fibonacci calculation. Here, SI initialization with 10, meaning the program will print first 10 Fibonacci number. AX hold the previous value starting from 0 and BX hold the current value starting from 1. These two registers will use to calculate display sequence. Let's move to the num part. This is next num part. This is a main loop that print the print and calculate Fibonacci number. First, we push AX onto the stack to preserve it before printing. Then we call the print simple function, which handle converting the number into ASCII and one printing it. After printing, we display the space using interrupt and our again and H again the readability. The next lines update the Fibonacci sequence next is equal to previous plus correct seeker. We when the decrement SI and if not 0, the loop repeat until 10 number are printed. This let's move to the next part of the code. This is a subroutine called print simple is responsible for the displaying number. It divides a number by 10 and quotient gives the 10 digit and remainder gives the 1 digit number. Then it convert both ASCII by adding the value of 0 and print each digit 1 by NINT by 10H again. This allows us to printing number like 13, 21 and 34 correctly on screen. Okay. Mm, This is, let's move to the output. This is our output. This is our output. That's it. This is our output. This is our output. When I assembled and booted this code, When I assembled and booted this code in a bush, this was our output. The program first displays a message Fibonacci followed by first 10 number of a Fibonacci sequence from 0 to 34. Each number is printed by using BIOS interrupt service directly from the boot holder without any operating system. Okay. In conclusion, the project demonstrate how low-level assembly can directly interact with the hardware through BIOS interrupt. I learned how INT10H for output manage registers efficiently and structure a bootable program that run entirely without an operating system. Thank you for watching my presentation. Thank you.